So I have to quit Zoom for a moment. I will come back.
Okay, fine, sir. No issue. You can leave, sir. You can rejoin. सर माइक म्यूट है। दीपक सर माइक म्यूट। हाँ बताइए सर, कुछ कह रहे थे?
मैं कह रहा हूँ किसी को कोई प्रॉब्लम आ रही है, कुछ इश्यूज हो रहे हैं? Anybody want to say something?
Hello.
Yes, sir.
Yeah. Host disabled attendee screen sharing. Can you enable that?
Okay, just wait a minute.
Screen sharing from my side.
Now, sir, check.
Yes, it's coming. Can you see it?
Yeah, fine, sir. Perfect.
So let me see. Fine. Yeah. Okay, so I think, are you seeing yourself in the screen?
Yeah, sir. Everything is fine now.
Everything. So no, I'm saying because on my screen I am seeing my slide as well as your video. So are you seeing yourself in the screen?
Yes, sir. Yes, sir.
Is this okay if for presentation?
Yes, sir. Fine. No issue, sir.
Okay. So today I will talk about some of my recent results on security of cyber physical systems against deception attacks in mostly in cyber physical systems. So why is it? So the problem is here. Oh, I can minimize this. Sorry. Thanks. So before I start, I will just briefly discuss the research topics that I am currently working on and some topics that I am planning to start working on in near future. And I'm looking for good MSR or PhD students to work in these areas where the students will require sound math skills for this kind of for working on this kind of problems. So one is deception attack on cyber physical systems, which I will talk about today. Network estimation and control problems, energy efficient sensing, energy harvesting, age of information, problems related to these areas. Then caching, cloud computing and data center networks, IoT network deployment, blockchain for IoT systems, specifically consensus, security and privacy issues, UAV network operations and deployment. This is a tentative topic. Radar signal processing, resource allocation and radar communication, and also federated learning and reinforcement learning. So I am working on some of these areas. Some I am planning to start very soon. Now, today's topic, that deception attack on cyber physical systems, it has potential application in lot of systems. One of them is actually security of smart grid. So, and I'm looking for funding in this area. So if some funder is interested, they can contact me. So with this, I will start my presentation. So I will try to cover 3 topics depending on the availability of time. The first topic is attack detection and secure estimation against false data injection attack in remote estimation. Number 2 is design of false data injection attack in distributed estimation. So the first one is security against false data injection. The second one is design of false data injection. And the third one is security of deep neural network-based image classifiers against adversarial images. So without wasting time, let me go to the first topic, which is security of cyber physical systems against false data injection attack. So this is a joint work with my postdoc advisor, Professor Urvashi Mitra, and some part of the work are also co-authored by Professor Erik Strom from Chalmers University, Sweden. And these works were published in these conferences, CISS, ISWCS conferences, and then finally it got accepted in transactions on control of network systems in IEEE. So, one question, one thing that I would like to mention is that if you have any question, you can ask me, but I cannot see if whether you are raising your hands or not. So, if there is any question, please stop me and ask me directly.
Sir, I think at the end of the session, we can keep there 15 minutes of question answer session.
So effectively, I have time up to 4:15, right?
Yes, sir. Fine, sir.
Okay, fine. Okay, so I think I will touch upon some of these topics. Maybe I will not go in details for each of these topics, but definitely the first topic I would like to elaborate. Okay, so so this problem, this security against false data injection attack, uh, this problem has a lot of applications in cyber physical systems, and here I am trying to motivate it through an example in vehicular network. Say, for example, in this picture, you can see that we have a number of cars. These cars are not ordinary cars, they are autonomous vehicles. They are equipped with many sensors and controllers. Suppose each of these cars is making some kind of measurement of their environment and then reporting these observations. Either they are sharing their observations among themselves through wireless channel, or they are sending their observations to a base station. The observations could be position, velocity, and acceleration of themselves, as well as the neighboring vehicles. So, and we are interested in some kind of network control of these vehicles. In a general cyber physical system, you could assume that instead of these cars, we have sensors. These sensors are reporting their observations to a remote node, to a sync node, which is denoted by this base station sign. So that goal here is to be able to track a spatio-temporal process by using these sensor observations. Now, typically, in this kind of cyber physical systems where you have sensors, then you have some estimator, which is located at this base station, and possibly this base station will send this the estimates to a controller, which will control the movements of these vehicles, or in general dynamics of a physical system. So suppose we have this such a closed loop cyber physical system or open loop cyber physical system. There could be many possible attacks to which these sensors are very vulnerable. So one class of attacks is called denial of service. For example, wireless jamming or packet drop attack. I will come to the description of packet drop attack very soon. The other class of attacks is integrity or deception attack, where basically the information flowing through this kind of network, they are compromised. The integrity of the data flowing in the network is compromised. So one possibility is replay attack, where basically if a particular sensor, suppose the first sensor is hacked, it will record some observation sequence that it makes, and then finally keeps repeating the same keep repeating to send the recorded observation to the base station. So this is called replay attack. Then there is Sybil attack. So where basically one particular node takes multiple identities. So one node pretends to be many nodes, and then they send false observation. And the third one is false data injection, which we will talk about today. So here what happens is that a particular node which is somehow compromised or hacked, it deliberately sends false data or false observation. It manipulates the observation. So let us try to zoom in into the false data injection attack as well as packet drop attack. So suppose we have 4 sensors or 4 vehicles. They are reporting their observations to a remote node, a remote estimator. So in false data injection attack, this particular vehicle, which is encircled in red, this vehicle or this sensor is somehow compromised, and it will send false observation, or it will misreport the observation to the remote node. Packet drop attack is a bit different. Here, this attacked vehicle will occasionally send garbage packets. So what do I mean by that? We know that in the wireless link between the sensor to the base station, we will have a wireless channel, and for that wireless channel, the packet error rate will depend on the signal to noise ratio in the link. So of course, you will never get all packets successfully delivered to the destination, because there will be some packet error. Now, typically these packet errors are identified by some kind of CRC checking in the packet. So CRC checks whether you have received some kind of garbage packet or not. Now suppose the transmitter itself is deliberately sending a garbage packet. Then the CRC check will detect that there is an error in the packet, but it will not be able to tell whether this error occurred because of the channel error or whether the error occurred because the transmitter itself sent a garbage packet. So if the transmitting node is actually under attack, then it can deliberately send garbage packets and pretend and so basically the uh, hope of the transmitter is that the receiver will actually assume that this error occurred because there was a channel error, and the receiver will not suspect the transmitter. So that's the hope of the transmitter. So let's look at the signal model closely in this case. It's a very crude model. So the received signal R is equal to the transmit signal X plus some ambient noise N or some thermal noise N, which is basically, which represents the case when there is no false data injection and no packet error. When there is false data injection but no packet error or packet drop, then what happens? The received signal is basically equal to X plus noise N plus some injected error E, which is deliberately injected by the transmitting node. When there is packet drop attack, or when there, suppose the packet sent from the transmitter to the receiver is in error, in that case, the receiver doesn't receive anything. It receives some null symbol because it cannot decode the packet. So this is the setting. So this kind of attacks are very prominent not only in autonomous vehicle or systems, but also in smart grid. In fact, you can see a lot of literature on false data injection attack in smart grids, and it can cause blackouts or accidents in the smart grid. It is generally relevant in any process monitoring and control application or in manufacturing systems. So for example, if you have a closed loop control system in a power plant, and suppose you have your temperature controller is using some estimate which is computed by reports coming from various sensors, and if some of the sensors are actually sending false data, then what could happen is that your estimate might be seriously wrong. As a result, the controller might exert a wrong control input, and it could lead to some kind of accident in the system. There could be a blast, for example. It is also useful in health monitoring systems or sensor equipments connected to a health monitoring network. So there are many applications. So in prior works, basically there have been a large number of papers on jamming replay attack. There are lot of works on false data injection attack. Very few works on packet drop attack, but there is actually no literature on the combined tackling of packet drop attack and false data injection attack, which we are trying to do in this work. So in false data injection attack, typically you can group the existing literature into 3 different classes. One class of problems, one class of works actually deal with attack design problem. So you are the attacker and you are trying to design some to perform the attack in such a way that you are not caught by the defense system. Then there is a line of work which mostly focuses on attack detection, and also there are works on performing secure estimation of the process in presence of these false data injection attacks. So, so in literature, there have been works on secure estimation under false data injection attack for an unknown attack sensor subset. There has been no attack actually. There has been no work actually. This paper, Liu et al., it appeared in 2017. So this assumed that the estimator knows a subset of safe sensors. So basically, the estimator itself knows that there are some sensors which it can rely upon. So it collects observation from those safe sensors and cross checks whether observations from other sensors actually they are matching with these observations. If there is a gross mismatch, then it can easily detect that there is an attack. But in this work, we do not assume any safe sensor. We assume that there could be safe sensors, but we don't know which sensors are safe. So this is a key difference between the previous work, which was done by Liu et al. And our current work. So our contribution in this work is that we have proposed some secure estimation algorithm under false data injection and packet drop attack, where no literature is actually available. So we have proposed a novel Kalman-like adaptive filter for secure remote estimation, which minimizes a cost that takes into account of three components. One is the performance under no attack. The other one is the error introduced by the false data injection, and the effect of packet drop attack. And we use simultaneous perturbation stochastic approximation, which is basically a non-standard, which is basically a variant of a stochastic gradient descent algorithm. But we have used a non-standard version of SPSA. So there is some novelty in the algorithm. We didn't take the algorithm blindly from literature. This algorithm involves multi-timescale update, and we prove desired convergence in absence of packet drop attack. So for purely under false data injection attack, we could also prove desired convergence. And we have shown that this algorithm actually has better numerical performance compared to existing works. Finally, we also proposed one attack detection algorithm for false data injection, which is just a heuristic. We don't have any theoretical proof for this, but we will show that it is actually performing fantastically compared to other competing algorithms in terms of attack detection. So, okay, so at this point of time, if you have any question, you can ask, because now I will start describing the actual system model. Is there any question? Okay. Okay, so let us start with the system model, with basically the system model of a remote estimation system. So suppose we have a bunch of sensors. There is a process xt, discrete time process, which is evolving as xt plus 1 equal to axt plus wt, where wt is Gaussian noise. These sensors are actually making some measurement of this process and sending the observations to a remote estimator. So YIT is the observation made by sensor I at time t, and this is equal to HIXT plus VIT, which is again, VIT is again Gaussian observation noise. This RI matrix is the covariance matrix, which is known to us. And the combined observations Y1 to Y4 in this case, they are collected, they are combined and denoted by this term YT. So YT is the collection of observations from all sensors at time t. So you can write YT equal to some matrix H into XT plus VT. VT is Gaussian. Based on this collected observations, the fusion center is estimating X hat T, or the remote estimator is computing X hat T. So this is the basic setting of a remote estimation system. Now let us see what happens when there is an attack. So in this picture, let's assume that the first two sensors are benign sensors. They don't misreport anything. They don't do any malicious activity. The last two sensors are malicious. Maybe they are hacked. So they can misreport their observations, and they can actually also send a garbage packet. We don't know which sensors are safe and which sensors are unsafe. So we don't know that the first two sensors are safe, second two sensors are unsafe. So when we assume that at a particular time, at most n0 number of sensors out of n sensors can be under attack. So this number n0 is known to us. We know that at most n0 number of sensors can be malicious, but we don't know which n0 sensors are malicious. So if there is false data injection and there is no channel error, then YIT equal to HIXT plus VIT from sensor I. This is the observation. When there is false data injection and no channel error, then actually your YIT equal to HIXT plus EIT. EIT is the injected error at node I at time t. And VIT is the observation noise that you are naturally getting. And if there is channel error or if there is packet drop attack, then simply you are getting phi. Now, we assume that sensor I has a known channel packet error rate, which is pi. And a malicious sensor on top of this channel errors, since it's sending additional garbage packets, so for those channels, for those wireless links, we will observe a higher packet error rate, which is denoted by qi. And actually, if you can watch this particular link, say suppose the last link is under false data injection and packet drop attack. So if you can observe this link's performance over a long time period, then you can figure out that the empirical packet error rate in this channel is much greater than the actual packet error rate, which is pi, which is the intrinsic packet error rate. So if you can find that, then actually you can figure out that this particular link is under packet drop attack. But we are doing something different because we are handling combined effect of false data injection and packet drop attack. Okay, so collectively in the network, you can write yt equal to hxt plus vt plus et, where et is the injected error. Traditionally, for these systems, people used Kalman filter for estimation and chi-square detector for attack detection. So chi-square detector basically computes the innovation involved in the Kalman filter, which is yt minus hax at t. So those who know Kalman filter, they know this. And then checks whether this particular quantity, which is a second order function of this innovation over a particular time window, if this particular quantity is greater than eta, some threshold eta, then we will say that there is an attack. Otherwise, it will detect that there is no attack. It will say that there is no attack. And this sigma z matrix is basically the steady state covariance matrix of innovation zt when assuming that there is no attack. So this kind of system was very popular earlier, but in recent literature, this paper in TCNS 2017, this authors Go et al., they proposed a linear deception attack, which can fool this chi-square detector. So what they did is they provided a linear transformation to this innovation ZT. Remember, this ZT is related to the actual observation YT. So if you alter this ZT, it means that essentially you are altering YT. So if you give a linear transformation to this ZT, keeping the distribution of Z3 unchanged, then this chi-square detector can be fooled. And the worst such attack could be the following, that you have some ZT, you just multiply it by -1. So you invert the sign of the innovation at a particular time. Then what will happen is this chi-square detector will remain unaffected, but the mean squared error at the estimator will be maximized. So the goal of the attacker is actually to maximize the mean squared estimation error at the estimator. And this attack is successful in doing that. Now, this was for a single sensor setting or under the assumption that all sensors are under attack. If all sensors are under attack, then this attack is fantastic because you cannot detect this kind of attack. But the problem is, if you don't have, if the attacker is not able to control all sensors, then this paper, Lee et al. 2017 papers, they proposed an algorithm which tackles this linear attack. But this paper assumed that they know a subset of safe sensors, which I was talking about earlier. So this paper assumes that there are a set of safe sensors, and I can actually cross-check observations from other sensors with this safe sensor observations, and I can figure out whether the other sensor observations are actually statistically matching with this sensor observations. So, okay, so now the problem in this work is that it assumes a subset of safe sensors. But in practice, that may not always be feasible. all of your sensors might be vulnerable, but in practice, what could happen is the attacker might have limited resources, so it cannot take control of all the sensors. So this safe sensor assumption is a problem which we tried to address in our current work, or in this work actually. This is the past work from my group, or from my side. So I will not go into too much mathematical detail because I understand that this is a broader audience and all of them may not have the necessary background. So, but I will try to give some intuition about the filter design algorithm filter that I have designed. So the mean square error at the estimator is given by this. It's averaged over time. Traditionally, Kalman filter is doing a linear filtering, x at t plus 1 equal to axt plus kt into yt minus ha x at t, where kt is basically the Kalman gain matrix. Traditionally, in Kalman filter, this kt matrix is updated without looking at the observation sequence. But in this work, actually, we have proposed an update scheme for this kt matrix, which takes into account the observations. Now, how should we do this? For that, we have to look at the filter design goals that I have listed here. So remember, Kalman filter is not optimal in our case, because Kalman filter is the optimal filter when there is no attack. But we are working on a problem where some of the sensors are actually under attack or can be under attack. So the goals here is that we have to design a filter which is robust to attack and which works well when there is no attack. That's number one criteria. Number two is, we assume that at most n0 number of sensors are under attack. So in this picture, suppose that there are 5 sensors altogether, and I know that at most 2 sensors can be under attack. Now somehow let some genie tell me that the blue sensors are under attack and the black sensors are safe. And suppose we know that information, then what will happen? If we collect observation only from these unsafe sensors and use them for process estimation using a Kalman filter, if the Kalman filter is collecting observation solely from these 2 blue sensors, suppose that observation is x hat bt, because B is a typical subset of size n0 in this case. So I am assuming that B is a typical sensor subset of size n0. So if I collect from this subset, collect observations from this subset B, and use those observations for estimation, then I will get x hat bt. Similarly, from the subset B complement, I will get x hat B complement T. If the 2 sensors are actually, if the blue sensors are not under attack, then you can expect that this x hat bt and x hat B complement T, they are close to each other. They will never be equal, but they are close to each other. But if there is an attack, then these 2, since the blue sensors are not giving you true observations, so definitely the estimate x hat bt will be very different from x hat B complement T. So this is the second intuition. Third intuition is, if there is no attack, then the packet error rate on any channel I, so from any sensor I, empirical packet error rate, which is denoted by this NIT, which is the number of packet errors from sensor I up to time t, divided by t. So this is the empirical packet error rate. It should converge to PI. PI was the intrinsic packet error rate of the channel, which is known to us. So if there is no packet drop attack, then actually the packet error rate, empirical packet error rate, will converge to PI by law of large numbers. But if there is packet drop attack, then these two will be different. So these are the intuitions based on which we are trying to design an optimization problem. So let us see. So basically what we are going to do is, we are going to formulate a cost function which involves these intuitions and then trying to optimize the cost function. So the cost function CT at time t is denoted consisting of three terms. One is this trace of PT. PT is the error covariance matrix at time t when there is no attack. So the first term is the mean squared error under no attack. Then we take a linear combination of the effect of false data injection and the effect of packet drop attack. So this lambda is a Lagrange multiplier. This term, which is max over all subsets, sensor subsets of size n naught, I am taking the difference between x hat b and x hat b complement at time t, taking square of the norm and taking max over all possible b. So if there is no attack, these quantities should be small because x hat b and x hat b complement should be close to each other. If there is an attack, then there should exist at least one b for which this norm square is actually very big, and that corresponding b will probably be the sensor subset which is under attack. This is the second term. We are calling it FDI detector. And the third term is actually acting as a PDA detector, packet drop attack detector. So here we are, this is a bit complicated function I'm not going to explain. So this captures the deviation of this empirical packet error rate from the intrinsic packet error rate PI. Now this is the single stage cost. C of this KT sequence. KT is your Kalman gain matrix at time t, and the expected single stage cost, which is a function of this KT sequence, is given by this time average of expectation of CT. Now, if the KT sequence is constant, means if you are using a constant gain matrix, then the time average cost is actually denoted by CK. So we are using this estimator, which is looking very close, similar to a Kalman filter, x at t plus 1 equal to a x at t plus kt into yt minus ht a x at t. The question is what should be the value of kt, the Kalman gain matrix. And what we are trying to do is we are trying to minimize the cost function c over this kt sequence, but we are not using a time varying kt. Rather our goal is to find a k-star value iteratively which satisfies this gradient of ck equal to 0. So basically I am trying to find a value of k for which the gradient of the cost is equal to 0, with the hope that this will minimize the cost, which may not minimize the cost because it can converge to a saddle point, but that is the intuition right now here. But the problem is this C matrix, the cost function, it's very difficult to calculate. We don't have any closed form expression. So how can we find this k-star? So for this, we have to use a theory called simultaneous perturbation stochastic approximation and use this to estimate the gradient of CK with respect to K and use that gradient in a stochastic gradient descent algorithm. So the intuition here is that this k-star should suppress observations or should ignore observations from attacked sensors. And it should do it automatically without knowing which sensors are safe and which sensors are under attack. So I will not go into detailed math. The SPSA algorithm is basically a variant of stochastic gradient descent, and it's used for stochastic gradient descent for high dimensional optimization problems. It's a computationally efficient algorithm. But as I told earlier, we are not directly using SPSA. We are using some variant of SPSA, which I will not be able to discuss in this talk because I have to cover some other topics as well. But there is a non-triviality in our application, in our applying SPSA to this particular problem. There are some computational issues that I handled because the computation was increasing with time, and we did approximations to correct that. And finally, we used SPSA to update this each entry of the KT matrix via a stochastic gradient descent algorithm. We used an asynchronous version of the SPSA algorithm because each entry of the Kalman gain matrix could not be updated at the same time. So this is an asynchronous algorithm. And there are some technical issues which we had to address. So basically, by using this SPSA algorithm, we tried to minimize the time averaged cost, which is a linear combination of the performance under no attack and the performance under attack. And this linear combination was characterized by a Lagrange multiplier lambda. Now, suppose that we are not interested in this minimizing this linear combination. Rather, we are trying to minimize the we are trying to optimize the performance under no attack, performance under attack, subject to a constraint on the performance under no attack. So, for example, in this function, so this is basically here we are trying to minimize the time average deviation between x at b and x at b complement. So this will give me an idea about the intensity of the effect of false data injection attack. So we are assuming that there is no packet drop attack for simplicity. So this is this first term, lim sup of this term. This is basically the time averaged effect of the false data injection attack on the estimation process. I want to minimize this subject to a constraint on the mean squared error when there is no attack. So the second term, this time averaged expectation of trace of PT, this is the time averaged mean squared error, estimation error when there is no attack. And I want to keep that within a certain bound P bar, because I have to minimize the mean squared error when there is attack, and I also have to constrain the performance, the mean squared error when there is no attack. And for this, we have to update this Lagrange multiplier lambda by using stochastic approximation algorithm at a slower time scale. So I'm not going to explain the technical details because that will take too much time, and that may not be the right thing to do for this audience. So if you are interested, you can definitely look at our paper, and I will be happy to take any query offline. So theoretically, what we could prove is, for a given lambda, this KT iteration is converging to the desired value of K, such that the gradient of the cost is becoming equal to 0. So this KT iteration is converging either to the either to a local minimum or a saddle point. And number two, for the common KT lambda T update, also we are seeing that this KT and lambda T updates are converging, iterates are converging to a desired set, which we originally aimed for. And to prove proving these theorems were not easy. You could see in the paper, there were actually many intermediate steps. We had to prove many intermediate results, and because the SPSA that we used it's a non-standard SPSA, we had to prove certain properties in this paper. Okay, so that's the theoretical part. Then we also proposed another algorithm for a false data injection attack detection. So the previous work was on performing estimation of the process under false data injection. Now we have attack detection algorithm. So I'm not going to give you the details of this, but I would just like to mention that this attack detection. Yes, is there any question? Hello. Is there any question? Okay. So this algorithm is actually some offline pre-computation, and it has to. The problem with the algorithm is that it is computationally very heavy. it has exponential complexity, but we will see that it performs very well actually. So this is motivated by the chi-square detector, but it is actually different from chi-square detector. Okay, so now for simulation setup, I will just briefly explain our findings in the simulation. We found that, so in these plots, actually you can see the blue curve is the mean squared error of our proposed algorithm as a function of time in a dynamical system. And these plots are actually other algorithms, that the horizontal lines. These are performances, time average performances of other algorithms. So we are seeing that our algorithm is performing better by several dB than these competing algorithms. This the line at the bottom, this pink line, this is the best performance that you could achieve in such a system. No other competing algorithm could achieve that, could achieve a mean squared error as low as that, but we are closer to that compared to other algorithms. So that's one finding. Then from the point of attack detection, we are seeing that our algorithm is actually significantly outperforming other detectors. So in these cases, in those two plots, I am showing the ROC performance, which is receiver operations characteristic plot for various detectors. So along y-axis, I am plotting probability of attack detection, and along the x-axis, I am plotting probability of false alarm. So this dotted line is the worst performance that you could achieve. Basically, you could achieve this 45-degree line by using a random coin toss. This red curve is basically the competing algorithm which requires safe sensors. This black line is the popular chi-square detector, and the blue line is our algorithm. You can see that for a given given false alarm probability, the probability of attack detection for our algorithm is much more compared to the other two competing algorithms. The only problem in our algorithm is that we have exponential computational complexity. But on the other side, if you compare it with the safe sensor algorithm, for this red curve, we do not assume that we know a subset of safe sensors. But this algorithm assumed that still they could not achieve as good detection performance as ours. Okay, so this is the finding. So now, to summarize, we proposed a secure estimation and attack detection algorithm under false data injection and packet drop attack. False packet drop attack is considered for the first time in the literature. We didn't assume any safe sensors available to us. We have used SPSA-based adaptive filtering, but we have used a non-standard version of SPSA with complexity reduction and theoretical motivations. We proved convergence proof for some cases. Numerically, we are seeing that this attack detection and secure estimation algorithms are doing much better than competing algorithms. And in future, as a future extension, we are planning to combine the detector and estimator to improve the MSE performance under no attack. And we are also looking for reducing the computational complexity of our algorithms. So this ends the first part. I will briefly go over the second and third talks. Before that, if you have any question, please ask me.
Sir, I have a question.
Huh?
Sir, I have a question.
Yes.
In your attack model, you have considered that all the sensors have considered the input as XT. It may,
No.
is
XT is a physical process. XT is a physical process. It could be temperature in this furnace. Y1, Y2, Y3, Y4, these are the sensor observations.
So my question is that whether it could be different for each sensor or same for all sensors?
No, the physical process is same for all sensors. but their observations could be different. See, what could happen is, suppose this xt is a vector. So maybe one component of the vector is visible to one sensor. Yeah, in a sense, it could be different. Yeah.
It
But
could be different,
this
sir.
model captures that.
Okay.
Sir, sir, one participant has asked, could you specify any application regarding this?
Yeah, of course. I mean, this is very much useful in smart grid, because in smart grid, see, typically what happens in IoT systems is that you send data packets, right? And traditional cryptographic solutions are not always useful for such systems, for security of such systems, because those cryptographic solutions require very long packet duration. Now you think of 5G applications where you have to ensure some latency constraint. You have to respect some latency constraint for the application, because it's a real-time control application. So you cannot afford to have very long packet duration. So your packet duration should be short. As a result, you cannot have cryptographic solutions. So your transmissions are vulnerable to this kind of false data injection attack. So for example, in smart grid, if the data packet that you are sending from your phasor measurement unit, uh, suppose someone has altered that data packet, so then you are getting wrong information about the amplitude and phase of electricity at that particular place. So that could lead to various problems if you are not getting the correct information. So one big application is smart grid. Another one is autonomous vehicles, which is coming up. And in general, for any cyber physical system, any manufacturing system, suppose you have installed sensors in a factory to monitor some process, and someone is kind of spoofing your sensors. So then this kind of problems are becoming relevant. Now I understand that this model is very idealistic, but in academia, typically we work on some problems which are mathematically tractable, so that we can get some nice intuition about the problem and later use those intuitions for real-time deployment, real-life deployment. Any other question?
Thank you, sir. Participant, any other question you want to ask? Anyone from the participants? So please continue.
Actually, I would like to take a maybe 2-3 minutes break, because I have to take some water and then
Okay,
start
okay,
again.
no issue, sir. No issue, no issue. Sure.
Okay, so can I start now?
Yes, sir.
Yes, sir.
Yeah. Okay, so the second part of the talk, so I think I have, how much time do I have?
Sir, around half an hour.
Half an hour, but there will be questions, right? So maybe 10 minutes for questions and 20 minutes for presentation.
Yes, sir. Yes, sir.
So I will not give as much details as I did in the previous talk, but I will try to give a brief flavor. I mean, some kind of flavor of the two problems that I'm kind of working on. So this work is actually again done with a BTech student Maulik Choraria and Professor Urvashi Mitra and Professor Eric Strom. It was published in Asilomar 2019 conference, and this extended version is going to be submitted very soon. So we have not yet submitted the journal version. So this is a bit different from the previous problem. So in the previous problem, the sensors were directly reporting their observations to a remote estimator. In this problem, we have a bunch of sensors. They could be vehicles or in the setting of autonomous vehicles. They are creating a multi-hop wireless network or a multi-hop network among themselves. So in a vehicular network setting, you could assume that each of these vehicles are equipped with one or multiple sensors. So if there are multiple sensors in a vehicle, you could club them and you could assume that there is a single sensor. There is a global process, physical process, which all these vehicles are collaboratively trying to estimate. They are doing to do it in a collaborative fashion. Hello? Okay. So what is happening here is that each vehicle is equipped with its own local sensor. It is making measurements by using those sensors. Also, each vehicle can at each time or at each round of communication at each time slot, a particular vehicle is allowed to exchange limited amount of messages with its neighboring vehicles. Say for example, this vehicle can exchange message with this vehicle which is its neighbor and this vehicle. So these two are neighboring vehicles to this one, but it cannot directly exchange message to this vehicle because maybe they are far apart, so they cannot exchange message directly. So now, so this kind of setting is again useful in general cyber physical systems for a vehicular ad hoc network smart grid. These links are bidirectional. You can these two vehicles can exchange message among themselves. There is a global process which the vehicles or the nodes are measuring, and they are exchanging their measurement or information with neighboring vehicles. And each vehicle has to estimate the value of the global process at a time, depending on its local observation and the message that is coming from neighboring nodes. Now, in this setting, suppose one particular node is under attack. So, for example, this particular node or vehicle is under attack, and someone is injecting false observation from this node. False observation to the sensors in this node. So then the problem is definitely this vehicle will make wrong estimate, but this false information will propagate to other nodes also, because other nodes are collecting information from this node. So the challenge here is how to model this complex dynamics. So I think I will not go much on prior work because there is very little amount of prior work. I will directly go to our problem, mathematical problem. So suppose we have a global process xt plus 1 equal to axt plus wt. Local observation at node k is ykt, which is equal to hkxt plus vkt plus ekt, where ekt is the injected error at node k. So for example, if this node is under attack, then we have injected error e4t at time t. So it's a Gaussian noise in process and observation as before. The key difference is each node is having its own estimate. Say for example, there is a global process xt. At time t, node 1 is also estimating x1 hat t. Here we have x2 hat t, x3 hat t, x4 hat t. This is the problem. And at each time, this node is having an additional false data injection attack, which is E4T. Now, this node is recording this processing this false injected error. It's processing that, and later it's sharing with neighboring nodes. So the neighboring nodes are also being affected by this injected error. So it is introducing error to all these estimators. So what we are doing here is we are assuming that the distributed estimation is actually done by a Kalman consensus filter. So everybody is familiar with Kalman filtering, which looks something like this. X at kt at node k is computing the estimate using this equation. X at kt equal to ax at kt minus 1 plus this term, which looks like a Kalman filter, and this is using the local observation at node k. This is using the local observation at node k. Plus there is a consensus term. The consensus term is basically checking, or it's kind of it's basically compensating for the difference between x hat k and the estimates coming from the neighboring nodes. So we have ck into a into this sum over neighboring nodes, x hat j minus x hat k. X hat kt is something that I am trying to compute. For that I am using x hat kt minus 1 from the previous time instant, and the estimates declared by the neighboring nodes in the previous time instance. So this is trying to enforce some kind of consensus among vehicles so that their estimates remain close to each other. So this is called Kalman consensus filter, which is now a standard estimation technique for distributed estimation problems. So now this GK is Kalman gain matrix and CK is consensus gain matrix. And suppose the attacker knows this GK and CK matrices, all matrices actually. Suppose the attacker knows. So we are focusing on linear attack, which I explained before. So we are assuming that at each node, the attacker is able to perform a linear attack. Under this setting, so we are using we are trying to do the following basically. We are trying to push the estimate at each node to a desired value, which I will come later. So basically, each node is trying to estimate the process xt, but we don't want that to happen because we are trying to attack the system. So what we are trying to do is we are trying to drag estimate at each node to a desired value, which the desired value is actually chosen by us. Now, the probability, now we should be careful. So when we are attacking a system, the attacker should be careful about not being detected by the detector deployed in the system. So what we are doing here in this formulation is that we are providing an upper bound of the attack detection probability in this setting, and we are actually tightening the constraint. So basically, suppose that we want that the attack detection probability PD should be less than equal to alpha. Say alpha equal to 0.5 or 0.05 or 0.1. We don't want the attack to be detected very easily. So if instead of using PD less than equal to alpha, I am taking an upper bound to the attack detection probability, and I am enforcing that this term should be less than equal to alpha eta by j. So basically, we are tightening the condition, the constraint. PD less than equal to alpha, that constraint is being tightened by this, which is a stronger constraint. So basically, our problem is that we want to design an attack which minimizes the deviation of x hat kt from a desired value x star. So we are trying to minimize this term averaged over time and summed over all nodes. So this term is summed over all nodes and averaged over time. So this should be minimized. So the deviation from each estimate from this x star, that should be minimized, subject to a constraint on the attack detection probability, but the attack detection probability is replaced by this stronger constraint. This is the constraint optimization problem. We use Lagrange multiplier lambda to obtain an unconstrained problem. And then we are updating on this attack parameters tk, sk, mu k, all these things by using SPSA. So basically, we have this unconstrained optimization problem, and we are using SPSA to minimize this this cost function. So this, yes, any question? Okay, so the unconstrained problem is solved by using SPSA. Uh, oh, shit. The unconstrained problem is solved by using SPSA at a faster time scale. And later, to meet this constraint with equality, we are updating this lambda t, which is the Lagrange multiplier. This is being updated using stochastic approximation in a slower time scale. So I will not go into the details of math now. So numerically, we can see the following. So let's, for example, let's consider this problem instance 1. So when there is no attack, then the deviation of the estimates from X star, or maybe I think it's better to take a different system, maybe the fifth one, where the things are more prominent. So for the fifth instance, the deviation of the estimates under no attack, the deviation from X star is actually 75.28 in this case. Under our attack, it has reduced to 46. So we are able to drag the estimates close to our desired value. And the attack detection probability is very small. It's just 0.0047. It depends on the constraint, because I think in this case, I have chosen a very small value of alpha. In this case, I chose a large value of alpha. For example, alpha equal to 0.3. So the attack detection probability is large. In this case, the attack detection probability is very small. It's up to us how to choose this alpha value, what value to choose. But definitely, whatever value of alpha I choose, I will get a detection probability smaller than that. Okay, so this is showing that the designed attack scheme is very successful in actually altering the estimates at all the nodes while not being detected by the attack detector. So is there any question on this? I will go to the third topic otherwise. Huh?
Sir, one participant has asked, how can we measure trust of a compromised node? How can we measure trust of a compromised node?
Trust.
Yeah.
See, here, as I explained earlier, we could simply use a chi-square detector. So the chi-square detector will check whether the observation from that node is following the desired statistics or not. Now, once the chi-square detector raises flag multiple times for a particular node, then you could actually put less trust on that node, because you know that probably this node is giving false data. So I will not consider this node when performing the estimation process. So provide assigning trust or trust scores on nodes. There is a huge literature. Say there, for example, suppose there could be one such solution. Say for example, one node. Suppose you have n number of nodes, and chi-square detector will also have false alarms. So suppose I keep counting the number of times a particular one alarm is coming from a particular node. Now, I can assign some kind of weight to each of these nodes, and the weight can be inversely proportional to the number of nodes, to the number of alarms that these nodes are raising. So through that, I can quantify the trust of a particular node, trustworthiness of a particular node.
Any other question, anyone?
Okay. Okay, so then I will quickly go through the third set of problems which I am working on. It's effective detection. It should be efficient. Okay, efficient detection of adversarial images. So this is a joint work with a bunch of undergrad students, Darpan, Kartik, Rahul, and Professor Indranaran Kar from our EE department. It is accepted in ACM AIMS 2020 conference, and the extended version you can actually find it in archive. We're planning to submit to a journal, possibly transactions on signal processing or transactions on image processing. Okay, so I will briefly explain the problem. So this problem is actually very relevant in security of cameras of autonomous vehicles or some kind of security monitoring systems. So in such systems, typically you have a camera. That camera takes an image and sends that image to a classifier which is based on deep neural network. So the DNN-based classifier classifies that image, and then that classification output is actually perhaps sent to a controller. In an autonomous vehicle, suppose there is the stop sign, and the classifier finds that there is a stop sign, so it will tell the autopilot or the driver uh, to stop the car at that particular time. Now, it is well known that these DNN-based classifiers are very kind of vulnerable to adversarial images. So suppose that somehow someone has hacked the camera, because in future IoT systems, you will see that each device will have internet connection and one IP address. So suppose someone has hacked that camera. So what they can do is they can add some intelligently designed noise to the pixel values of this image. So stop sign is the original image here. You add this noise, the resultant image still looks like stop image to human eye, but the classifier will misclassify. It will say that this is a teddy bear. Similarly here, you have ice cream plus noise. The classifier tells that this image is the image of a bucket. So what we have done in this work is that we have performed some pre-processing scheme. We have provided a pre-processing scheme before feeding the received image to the DNN-based classifier. And for CIFAR-10 dataset, we have shown that this has very high attack detection probability and low false alarm probability. So we have only done detection. We have not worked on cleaning the image, only detection. I will not go into prior works now. So since I don't have much time, I will try to give a brief overview of our first algorithm. So basically, we have proposed two algorithms. One is this PART, and the other one is an adaptive version called APART, which is an enhancement on PART. Actually, APART is the best algorithm that we have seen, but it's a bit complicated. So to avoid that, we will mostly describe the PART algorithm. The problem with PART algorithm is that its runtime is its computational complexity is more. APART is very much feasible in practical systems, and it has very good performance. But due to avoid the technicalities, because APART has some stochastic approximation updates for the training phase, and I don't want to go into depth of that. So let me see. So what we have seen here is that each DNN-based classifier is actually having a set of decision boundaries. So, for example, suppose there are two kinds of images in the world: dog or cat. So you can imagine that your image is actually a collection of pixel values which could be written as a vector. So now your received image is actually a vector, and for each image, so basically now since you have only two kinds of images, dogs and cats, so you have to map every image into one of these two classes. So on the n-dimensional space, suppose n is the length of the vector, on n-dimensional space, you have to draw a decision boundary that on this side of the boundary, whatever I receive, I will call it a dog. On the other side of the boundary, Whatever vector is received, I'll call it a cat. So that is typically what is happening in DNN-based image classification. So you have decision boundaries. Now, typically what people have seen, there are two key observations. One is, I think, not this. So one is that in these images, in the adversarial images, the modified adversarial image actually is lying very close to the decision boundary, because the adversarial image is designed in such a way that it's not distinguishable to bare human eye. So definitely, if it is, suppose the image of a dog, uh, suppose I modify that image into another image, which is very deep inside the decision boundary of the cat image class, then it will be detectable by bare human eye. We don't want that. So I will design the adversarial images in such a way that it has just crossed the decision boundary, but it has not gone far beyond the decision boundary. That's one observation. The other observation is that because of this, uh, the most of the information in an adversarial image is, so basically not in an adversarial image, in an ordinary image, most of the information resides in the first few principal components. If we do a principal component analysis, the most significant components are the ones which will determine whether this image is of a cat or dog. But in case of adversarial image, the adversary or the attacker is not trying to alter the most significant principal components, because it knows that if it does so, then the detector will be able to detect it very quickly. So it actually alters the least significant principal components of the image. And as I already mentioned, that these attacks intend to push the adversarial image close to the decision boundary to fool the classifier. Okay, I think this is a pictorial representation. I don't want to go into details. So what this part algorithm is doing, that in the training phase, it has a training image set. It performs a singular value decomposition of that image training data. It sorts those singular values in terms of ascending to descending eigenvalues. Basically, it is performing principal component analysis, and it finds the principal components, the eigenvectors of the positive semi-definite matrix that is involved in singular value decomposition. Now, in test phase or online part, suppose you have an input image. So you do the following. You first feed this image directly to your classifier and get the original category. Now you project this image, and as an alternative path, you project this image onto these eigendirections denoted by U. So you perform the dot product. So basically, from the pixel domain, you converted the image in the pixel domain to another signal in the in the spectral domain. So you sample and add C-dimensional Gaussian noise, where C is our design parameter. So basically, you do it to the least significant components. Then you perform an inverse transform to get back the image in the pixel domain and feed it to a classifier. So basically, what you are doing is you send the original image to the classifier, get the output, and then convert this image to spectral domain. In the spectral domain, you randomly perturb the least significant components by some Gaussian noise. And then from the spectral domain, you again take inverse transform to get a perturbed image in the pixel domain. And then feed that perturbed image to the classifier. So the goal here is that since I know that my image is the adversarial image can be very close to the decision boundary, the hope here is that if I randomly perturb it, it may cross the decision boundary again. So now you feed this perturbed image to classifier, get the output. Now suppose this output and this output, they are matching. Then fine, then you can say that this is not adversarial. But if they are not matching, then you can actually guess that these images are close to the decision boundary, and so they might be adversarial. So if there is no difference, then it is not declared as adversarial. If there is a difference, then you actually keep perturbing and checking it. Now finally, if I get beyond a predetermined time capital T, if I keep getting this thing, so for example, I perform this and I find that after T number of perturbations, I have not seen any change in the level from this to this. So there is no change. Suppose I observe that I have perturbed it T number of times, but I have not seen any change in the output of the classifier. Then I can be very sure that it is not adversarial. But if I get at least one change, then I can declare that it is adversarial. So this is the part algorithm. And APART algorithm is actually a very an advanced version of this. It has mathematical intuition. So basically, I want to minimize the number of perturbations of the image subject to a constant on false alarm probability and probability of misdetection. So false alarm everyone knows. So it's positive, this is false negative. So this is false positive, this is false negative. I want to constant both false positive and false negative, and at the same time I want to minimize the number of perturbations so that the computational complexity remains small. Because perturbing the image and feeding it to a classifier, it requires computation. So again, I relax it by a Lagrange multipliers, learn those Lagrange multipliers, use SPSA, all these things are done in the training phase. And one key feature of this APART algorithm is that it is motivated by the sequential probability ratio test in detection theory, and it keeps two threshold values. So it's a two threshold algorithm. So this particular quantity is actually calculating the likelihood of a function of an image to be adversarial or non-adversarial. So if this quantity is high, then it's more likely that the image is adversarial. So we have actually calculated two threshold values. One is higher threshold, the other one is lower threshold. So the algorithm works as follows. If this, I calculate this quantity, if it is above the higher threshold, then I will say that the image is adversarial. If it is lower than the, if it is smaller than the lower threshold, then I will say that this image is not adversarial. If it falls between those two threshold values, then I am undecided. I don't know whether the image is adversarial or the image is not adversarial. In that case, I will again perturb that image, and I will try to see whether this ratio goes above the threshold or below the lower threshold. Okay, so I'm not going into details. Yes, I think this is important. So this is a small illustration of the performance of our APART algorithm and another algorithm GPRBD in the literature. So we are plotting detection probability versus false alarm probability. The red line with blue marker is our APART algorithm, best APART algorithm. Blue line is basically the PART algorithm, and the black line is some other algorithm from standard literature. And you can see here that APART, actually in various plots I have seen that APART is performing better than PART. or maybe they are very close to each other. For the same false alarm probability, I am getting higher detection probability for part and apart. And the black line is providing much lower attack detection probability for the same false alarm. Sorry? Hear properly. I cannot hear properly. Can you speak louder? Can someone convey the message to me?
No need, sir. Could you please write your query in the chat box? No need, sir.
Maybe then I will come back after the talk, after I finish this. So
you can write your question in chat box.
So this is the performance of performance improvement under part and apart, as I said.
Okay.
Then in the next, in this plot, actually we can see that the computational complexity of apart is actually very small compared to the part. So for example, I think mean number of samples or perturbations that you need. In one typical example, you are some kid is talking. Who is this? Okay. So mean number.
Okay.
Participant, please mute your mic. Participant, please mute your mic.
Okay, so so in this case, you can see, for example, in this case, part is taking 25 perturbations, or maybe maybe I will take a better example here. Part is taking 11.86 perturbations. Apart is taking only 1.42 perturbations on an average. So the computational complexity is very low in apart compared to part. So that's all. I think, yeah, I think this is a better example. Here you can see that part is taking, for this case, part is taking 13.3 perturbations on an average. Apart is taking 1.85 or 1.92 perturbations for two different variants of apart. So it is taking slightly more computational complexity than this GPRBD algorithm. For example, the runtime in GPRBD is smaller than apart, but as we saw earlier, we are compromising with the runtime in apart algorithm because we are getting much better detection performance under apart. But part has much higher runtime, so it is not a very practically feasible algorithm. But part was used as the initial building for developing this apart algorithm. Okay, so I think with this, I will just summarize the third talk. So we proposed a novel preprocessing algorithm for detecting adversarial images. It has really low computational complexity. It is motivated by SPRT-like algorithm, sequential probability ratio test, and we are using SPSA to determine threshold in the truth threshold policy. We have a mathematical framework for our algorithm, which is very rare in this literature. This scheme is agnostic to attacker and classifier models, which is actually a very big achievement for our work. And numerically, we are able to show that it's outperforming existing algorithms, and I have shown one such plot. So with this, I will conclude. Now I am ready to take questions. I'm sorry because for the last talk I had to move fast, but I wanted to give a glimpse of what I have done in this area, and I'm hoping that the audience will have the motivation to go back and look at the literature in this area, and they will hopefully perhaps start working in this area. So with that, I would like to thank everybody, and I will be happy to take any questions. Let me see the chat box now. Okay, so now the problem is I cannot. So somehow this Zoom bar is minimized. So what I'm doing is I will log out and again come back to Zoom. Okay, or
sir, someone is asking about principal.
Now I could open the chat.
Yeah.
So which question should I answer? I think the recent ones, right?
Mr. Prakash has asked about principal component analysis.
Principal component analysis. I think principal component analysis you can get in any standard machine learning book. For example, Bishop's book you can get. So it's basically suppose you are getting multiple vectors and you want to find out along which direction these vectors or these data vectors are having the maximum amount of variability. So what you do is you calculate the standard covariance of this vector and then perform a singular value decomposition or eigenvalue decomposition. Now, the largest eigenvalues will give you the principal components, and the corresponding eigenvectors will give you the directions corresponding to the principal components. This is the rough idea is like that. So you can go and check in any standard machine learning book, or you can search on internet. You will find that. It's a very standard thing, textbook thing.
Sir, I have a doubt.
Yeah.
Sir, your last algorithm that you have used in part and A part, in that, can we use some kind of blind source separation?
Blind source separation. What do you mean by that here?
Means I can use the blind source separation so that I can separate out the this it contains noise or not noise or some
Yeah, I mean, I'm not very familiar with that. I mean, can you give me one illustration of an algorithm? I mean, how this algorithm operates here?
Suppose in the case of blind source separation, there are multiple speakers there in the room, and they are speaking at once. So from the blind source separation, we can separate out that which one speaker is for speaker 1 and which one is speaker 2. So
speaker 1, speaker, that is audio.
Yeah. So can we use that kind of algorithm here?
Yeah, I mean, I honestly speaking, I am not familiar with speech processing literature, so I cannot comment on that.
Okay, fine. No issue.
Maybe definitely once since you have raised this, I will look at the literature and see if it is applicable here. Because at least in adversarial image literature, I have not seen any such work. People are directly using deep neural network based classifier. I mean, blind source separation is, I mean, I have heard this term, but probably this is a classical signal processing technique, right?
Right.
Yeah. So I'm not familiar with that because I don't work in that area.
Fine, sir. No, thank you, sir.
Thank you, sir. Sir, very informative session, sir. Thank you.
Thank you.
Thank you.
Thank you,
Thank
sir.
you very much, sir.
So there is no other question?
Sir, we need the PPT slides of this session.
Sorry?
PPT of this session. PPT.
You need slides?
Yeah, so these PPTs, your PPT. This thing you have to upload on the IITD website.
So I'm there is some problem. I cannot hear him properly. So do you need the slides?
Yes, sir.
Okay, fine. I will email it to the organizers.
Fine, sir. No issue. Thank you, sir.
Okay. Thank you.
Okay, sir. Thank you, sir. Thank you, sir.
Thank you. Thank you. Thanks to all of you for inviting me. I hope it was useful to other people, the participants.
Yes, sir. Sir, very informative session, sir.
Okay, I was a bit superficial because I had to cover too many things. Thank you.
Thank you.
This is from IT department, Galgoja College of Engineering and Technology. We are gratitude you for this session by providing you this certificate.
Oh, thank you. Yeah, so you will email me this.
Yes, sir. Definitely, we will mail you too.
Thanks a lot.
Yes, Bhavna ma'am.
Thank you.
Thank you, sir. Thank you, sir.
Bye.
Okay, sir. Yeah.
Huh?
Nothing, sir. Nothing. Yes, tomorrow's session will be started at 10 a.m. sharp. So I request to all the participants, please join before 10 minutes, around 9:50 a.m. tomorrow. And there are total 5. This is 5 days FTP. So one participant has asked about feedback and link. So your exam and feedback will be provided at the last day. On the 5th day, at the last session, you will get feedback, and there is also 1 hour exam session. So as per AICT rule, 80% attendance and 60% passing marks is mandatory to get the certificate. So make sure then all the participants are participating here by their registered name, and they are attending all the sessions, because this certificate is provided by you by the AICT. So continuously they are watching and monitoring in each and everything. So if you are attending all the session and clearing all the exams at the 5th day, then you will able to get the certificate. So I request all of you, so please attend all the sessions for maintain your attendance as per AICT expectations. Deepak sir, you want to say something?
Hello, sir. Hello, ma'am. There is no separate feedback link to for every each day.
No, 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 no. We will provide you as a common feedback on 5th day.
Ma'am, how come then you can take attendance for every day?
Ma'am, it is automatically your time session and what time you logged in and what time you are leaving from this session. That automatically is recorded here. We will check from there only.
Okay, thanks a lot, ma'am.
Okay. Deepak sir, you want to say something?
session करते हैं खत्म फिर.
Hello, there is any YouTube link, ma'am? Ki only Zoom link only.
Sir, actually there is some problem in this platform. We are trying to doing this online also in YouTube. Maybe possible tomorrow's session will be also online in YouTube.
नहीं मैडम, ये लास्ट वाला जब हम पूरा कर लेंगे ना, then we will upload all the videos on our channel.
नहीं सर, नो सर, ही इज आस्किंग अबाउट कि इस चैनल इस सेशन के साथ साथ आप करें लाइव भी है यूट्यूब पर या नहीं?
नहीं.
So we will trying for that. Maybe possible कि tomorrow session will be also we are providing you online link of YouTube. Any question from anyone? Any query? Participants?
Anyone?
Hello, ma'am.
Yes, sir. Tell me.
Ma'am, my question is like as discussed in the morning, I wanted to go through the videos whatever you have taken the recorded, so that we can prepare accordingly for the next day, and the contents whatever are taught, for an hour I have missed the session because of my lecture. So I just wanted to go through the same contents again, and I can prepare for the exam later. So for the entire evening I can just go through whatever content I have missed. So that is my question.
Actually, sir, what I have to do, we will record all these sessions and we will upload after completion of this FDP as per AICT guidelines. Before completion of FDP, we cannot upload any videos anywhere. Even we cannot share any video.
And that also, that link.
One request to you, please share the today PPT on the WhatsApp group, please, ma'am.
If the speaker will provide us, if the speaker will provide us, definitely we will share, sir.
Because it would be helpful for us to prepare for the entire tenure, and we can be ready for the exams as well at the end.
Sir,
that is
one more request, Gaurav sir, that if you are attending your lectures, then how can you attend here this FDP? Because attendance is mandatory is here. So you have
actually that was actually that was urgent lecture, because in the next session the students will be having a practical examination. So for an half an hour I wanted to conduct that, and that was the reason I could not attend that session. So that was my query actually. Okay. Henceforth I will be attending entire session regularly. You can check my attendance as well later. Okay, but that was my urgent.
No issue, sir. No issue. Once we will get all the PPTs from speaker, we will share with you.
Okay, ma'am. Thank you.
Deepak sir, you want to say something regarding? Anyone wants to ask anything?